So in this chapter, we're going to talk about Taylor and Laurent series. Taylor series are inevitably something that you've seen before, but we're going to add in all the stuff that's relevant for a complex series. Laurent series will be new. We'll talk about that in the last half of the chapter. So for now, let's just concentrate on Taylor series. And what I want to do first, before we get to Taylor series, is a few facts about series and holomorphic functions. So the first one is that, and so this is going to be a theorem from the book. So let's let say f has a power series. So let's let f of z be this power series, c sub n, z minus z naught to the n, as n goes from 0 to infinity. And suppose that this power series has radius of convergence. So it has radius of convergence r. Okay. Then it turns out that f is holomorphic inside the radius of convergence. So it's holomorphic on the disk centered at z naught of radius r. And moreover, the derivative is exactly what you think it is. It's the derivative of the series if you just differentiate it as a polynomial. So this is the derivative of the series. So we're going to go from 1 to infinity, c sub n times z minus z naught to the n minus 1. So this is n times z minus z naught to the n minus 1. So we're differentiating z minus z naught to the n just as a polynomial. So the exponent comes down, subtract 1 from the exponent. And then we lose the first term because it was constant. So that's why the sum starts at 1. Right? You can, I mean, there's nothing wrong with starting the sum at 0. It's just that the first term is 0. So this theorem actually says a lot. And it's kind of, I'm grouping together two theorems from the book. So the first thing we need to do is to prove that f is holomorphic. And then once we know it's holomorphic, then talk about how do we get the formula for the derivative. So there's going to be two things that we'll prove here. Okay, so first we'll show f is holomorphic. Okay, so that's our first goal. So first we'll show f is holomorphic on this disk. And to show that it's holomorphic on this disk, what we're going to do is a few things. So first I want to recall Moraris theorem. So call Moraris theorem, Morera theorem. This is an M, by the way. So Moraris theorem. And what Moraris theorem says is that if f is continuous on G, so if f is continuous on G, and if f satisfies that this integral is 0 for all piecewise smooth closed curves gamma in G, then f is holomorphic in G. Okay, so this is something that we talked about back in chapter 5. So then f is holomorphic in G. So this we talked about back in chapter 5. I don't remember exactly what theorem it was, but it was in there. So this is something that we've seen. So we're going to use that. So we want to obviously show that something is holomorphic. So we're going to first show that it's continuous. And then after that, we'll talk about why the integral is 0 for all piecewise smooth closed curves. And the idea is pretty simple. So we're going to use uniform continuity here. And notice that we have a power series that has a radius of convergence capital R. And so just remember the picture. I think this will help us. So we have Z naught. We have a circle that's, say, radius R away from Z naught. And then remember that this is an open disk, so we're not including the boundary, but any closed disk inside this region. So if I have any closed disk inside this region, the function is going to be uniformly continuous on that closed disk. Okay. So notice that for any value, let's call it little r, that's less than big R, f is uniformly continuous, uniformly convergent, I'm sorry. uniformly continuous is not a thing, but uniform convergent on that closed disk centered at z0 of radius little r, where little r is just less than big R. Okay, so this is something that we talked about back when we talked about the existence of a radius of convergence. So this is an old idea again. But once we have uniform convergence, then everything is nice. So by uniform convergence, so in this disk, this closed disk of radius little r, since f is uniformly convergent, and since each of the terms is continuous, it follows that f is continuous, because we proved, one of the things that we did in detail in chapter 7 was we proved that if we have a bunch of continuous functions f sub n, and if they converge to some function f, then that limit function f is also continuous. In other words, uniform convergence implies continuity. This is something that we talked about in chapter 7. So that gives us continuity of this power series. Okay, so that's the first thing. So that's continuity. The other thing we're also going to use this uniform convergence on, and this was on the what I called the third part of that same proposition. Okay, so here the idea is that if you have uniform convergence, then the integral in a sum can interchange, and in particular the integral over a closed piecewise smooth path in G is 0. So this is something that we also talked about actually in the same theorem. So we're just using this different parts of the theorem over and over. So also by uniform continuity, it turns out that if I look at the integral of the sum, so this is the integral of the sum as n goes from 0 to infinity, c sub n z minus z naught to the n dz. This is going to be the same. You can interchange the integral in the integral in the sum, and in particular, you're going to get 0. So again, you can interchange the integral in the sum by uniform continuity, and then the integral is 0, as we've talked about many, many times. Right? If you integrate z, so hopefully you remember that we spent what seemed to be an inexplicable long time on this. But if you take, so I guess I might as well write more details here since we did it all. But if you reverse the order here, this is the sum as n goes from 0 to infinity, is the integral over gamma. And then you have some constant, which actually you can just pull out of the integral. There's no need to do that. And then we talked about how do you evaluate z minus z naught to a power. And if all the powers are non-negative, then this entire, all of those are entire, and this integral is going to be 0. Okay, we actually handled in even more detail what happens when n is a negative integer. And the only thing, the only value of n where we get a non-zero integral is when n was -1. But here we only have n going from 0 to infinity, so all the integrals are 0. In particular, the sum is 0. And since this is true for all curves gamma, so now I'm doing, there's two more things that I need to say here. The first is that what we said so far was true. So I specifically applied it to gamma being this circle. But then what we're allowed to do by Cauchy's theorem is that since we know that we just proved that this function is holomorphic, so by Cauchy's theorem, we're allowed to deform by homotopy, the Cauchy's homotopy theorem, we're allowed to deform this curve into whatever curve we want. Okay, so that's how this follows from that. So this is true not just for the circle, but actually for any deformed version of the circle, any simple, any closed piecewise smooth path gamma, this is going to be true. And therefore, by Moraris theorem, f is holomorphic. Okay, so that's how all of those pieces fit together. So f is holomorphic by Moraris theorem. Okay, so that's the first big piece of this of this section is that if you have a power series, then it turns out that a power series is always going to be holomorphic inside its radius of convergence.